Okay, hello everyone. Let's go ahead and get started for the day. As I'm sure you're all aware, the big topic on our agenda for today is getting ready for the exam that is coming up later on this week. So I'm just going to start off with a few minutes just to go over the logistics. The good news is that it's the same as it was last time. So you will be reporting to the same room that you went to take the first exam. The room numbers are still here. If you need to refresh your memory about where to go, you are allowed to bring a sheet of paper with you that has notes on it, both front and back, just like you did last time. So any regular size sheet of paper is fine. You can type it, you can write it, whatever you want to do. You are not allowed to use electronics, so no calculators, no phones, nothing like that available during the exam. Be sure to bring your ID and a pencil. There's not really much else for me to say in terms of logistics. The only other thing that I really want to make sure you're aware of, I mentioned this before, but I really want to make sure everybody knows that the material that we just did last week, Module 7 regarding objects, that is not going to be on the exam on Thursday. That will be on the following exam. The exam that you're going to be taking on Thursday is going to cover Modules 4, 5, and 6. So Module 4 was over APIs, drawing, standard draw, stuff like that. Module 5 was about methods. And then Module 6 was over recursion. Objects are not going to be on this exam. They will be on the next exam, so you do not need to study that material for the exam on Thursday. Does anybody have any questions about the logistics, about where to go or what to bring or anything like that before we hop into code stuff? Any questions at all that I can address? Okay, so then as I hope you have seen, I put out some materials to help you prepare for this exam. Just like for the last exam, there is a practice quiz on Canvas that has a bunch of multiple choice and fill in the blank style questions that you can use to practice. And then I also posted a practice repository that has code reading questions and code writing questions that you can use to practice for the exam. I am here to help you study in whatever way would benefit you the most. So at this point in time, I'm just going to open up the floor. Anybody who would like to see me work through any of the problems, I'm happy to do that. If you just have more general conceptual questions, happy to talk about those. Whatever at all you need, now is the time. Yeah, in the middle there, in the back. The code writing question? Sure, yeah. Okay, great. Awesome. So this is one of the ones where I gave you an image and I'm asking you to write code to replicate that image. So let's take a look at the picture first that we're trying to mimic. We see that I've got a box, and then I see this pattern looks like it moves out in 4 different directions: the upper left, the upper right, the lower left, and the lower right. This is the problem, I believe, does ask you to use recursion. Yes, it does say you have to use recursion. So let's talk about that for starters. Recursion is a topic that is going to be on this exam. That is true. It is only one of the 3 topics that we've covered since the past exam, however. So one thing that I see on this exam is students tend to overdo it with recursion a little bit. You do not have to use recursion on every problem. In fact, I try to be very, very, very clear about the problems that you do have to use recursion on. And if I do not say that you have to use recursion, then you do not have to use recursion. You can and should use a loop. Don't make these problems any harder on yourself than they have to be. I try very hard to be clear about that when I can. I still see students using recursion when they don't have to. A lot of times that's just going to make it more difficult. In this particular case, though, I am telling you you have to use recursion. And in fact, I think it would be pretty tricky to approach this problem without using recursion, because this is one of the categories of problems that we introduced you to during Module 6 Recursion Week. It's a divide and conquer problem. So these are classic problems that work very well with recursion. Another example that you saw was the circles problem in the studio, where you're drawing circles on the screen. It's a very similar kind of problem. The max path length problem from the assignment is also a divide and conquer problem. What makes them divide and conquer problems is the fact that I see the pattern appearing more than once. So the pattern that's being drawn here is appearing 4 times. So that means that I expect to see 4 recursive calls in my code, once for each of the 4 directions. So the dividing and conquering is going to match whatever problem it is that you're trying to solve. For max path length, I had to check the path length in 4 directions, so there were 4 recursive calls there as well. But for circles, I think you only had to do it in 3 directions, so that I would only expect there to be 3 recursive calls there, right? You have to match the number of recursive calls to however many directions you're moving off in. So in this case, I would expect to see 4 recursive calls. And the other thing to talk about with these kinds of recursive problems is what's the base case? So that's a very interesting question for any recursive problem. But when it comes to the recursive problems that involve drawing images on the screen, the base case is almost always going to be related to the size of the shapes that are being drawn. Essentially, when it gets to be so small, after a certain point, the shapes I'm trying to draw are so small that I'm probably not even going to be able to see them anyway. So I might as well stop. That is almost always going to be a base case for these kinds of recursive drawing problems. So let's go ahead and take all that information and start trying to piece together some code. A lot of people like to start off by coding with the base case. So let's take a look at what parameters we have available to us. I've got 2 parameters up here. It looks like an x coordinate and a y coordinate to specify the center of a square to be drawn, and then this one over here is related to the size of the square that I wish to be drawn. So since the base case is based on the size, right? I'm probably going to use that half length to determine when I should stop or continue. And so you might say something like, if the half length is less than 0.001, call this the base case, right? Otherwise, we'll do some recursion. So here, you might be saying, where did this come from? I just chose an arbitrarily small number on an exam problem. I might tell you what this number is. If I don't tell you what it is, just pick something that's arbitrarily small. I'm not going to count points off because you didn't have enough zeros after the decimal point. That is not what I'm worried about. I'm worried about, does your base case stop when the image gets too small to draw? Do you have the right number of recursive calls to perform the actions? So let's talk about this base case a little bit more. What do I want to do? If I hit the base case, the thing that I've gotten to is too small to draw. What do I do here? Ah, that's an interesting answer. The answer I heard was return. Let's talk about this for a second. I think this is an important concept relating to methods. Return does 2 things for us. A return statement does 2 things for us. It says, this is the answer. This is the result. This is the value that represents, the result of whatever this method has done. But in this case, we're actually not using it for that purpose, right? You can see that the return type is listed as void. So for a method that is given as a void return type, a return statement can't actually return anything. So here, this return statement is being used for another purpose. A return statement also says, we're done. The method is over. You should stop, right? So if a method is marked with a void return type, I can't actually return a variable or a value or a number or anything like that. But return statements still can be used to say, stop, we are done. We are finished. There's no more work to do here. That is still a thing that's possible to say. I do think, though, it's interesting. If there truly is no more work to be done here, this could be rephrased a little bit as well. In fact, I would probably be more likely to say something like this. If the half length is bigger than this, then do some recursive stuff. If the half length is less than this, well, then I'll just skip over all the recursion and do nothing, and the method is over, right? I don't have to say return or else or any of that stuff. This is equivalent to what I had up here before. And I would accept either one as a possible answer. That's fine. Two different ways of saying the same thing. Regardless of how you approach the base case, though, it's now time to do the dividing and conquering part. So we're going to have 4 recursive calls. It's important to look at the image, keep in mind what information you have available to you, and then think about where you're trying to go next. So the information that I have available to me is a center point and a half width for this big square in the middle. And from there, I need to go in 4 different directions, but I'm just going to focus on going up and to the left for starters, and then I'll worry about the other 3 later. So from here, I need to get to here, to this square. So it looks like it's going to be 1 half width, 2 half widths to the left, 1 half width, 2 half widths up. And then the overall width of the square appears to be going down by 1/3 based on what I'm looking at in this image, because this is the same width as the big square, and I can see that this square is roughly 1/3 of that. But let's just try and code it up. I'm going to do 1 recursive call for recursive carpet. I'm saying that the x position going up and to the left is going to be from my current x position. I need to go left, which is going to be subtraction from my x coordinate, 2 times the half width. Is it half? What's it specified as? Half length? Sorry, half length. The y value is going up, so I'll be adding to my y value. And then the third parameter is the size, and I was saying that I think the size is being divided into thirds. So the width of the big square to the width of the small square, it's getting shrunk by 1/3 every time. I've actually forgotten one very important step, which is to draw a square. So I actually need to draw, right, when I call it the first time, I need to draw this big square. And then on the first recursive call, I'll draw this square. And then on the next recursive call, I'll draw this square, and so on and so forth, going up and to the left. So let's draw the square. That will just be a call to standard draw dot filled square. There we go. Plugging in the values for our x coordinate and the size as parameters. We're now ready to test this out. Now again, on an exam, I fully understand the fact that you're writing this out on a sheet of paper, right? And you don't have the ability to stop in the middle and plug it all into Eclipse and test it out and see how your work's going. I realize that, but we do have that ability now, and I think it's useful to help us understand, so there's no reason not to do that. All right, so it looks like it did move up and to the left. This square in the middle is awfully big. I think what I might do to see if I can fit this in a little bit, I think this is the starting values down here, and I think that I might have made this starting value for the square just a little bit too big. So I'm going to shrink it a little bit. I'm going to make it a little smaller and see if that allows more of the picture to fit on the screen. I think it was working. I think it was just not fitting it all on the screen. So let me shrink that and see. Okay, that looks better to me. Question in the back. Uh-huh. Mm-hmm. You can't. No, it's just not possible. So instead, what I would encourage you to do is understand that I am not testing you based on whether you can match the image specifically. I'm testing you based on, do you have a reasonable base case? Do you have 4 recursive calls going in the proper directions, right? If you get the numbers off a little bit, oh well, you know, as long as they're in the right ballpark, then that's not what I'm worried about. So I hope that helps. Yeah. So yeah, this takes care of this condition going into the upper left corner. You can see the squares being drawn in the upper left corner. So, you know, the good news is that the other ones are going to follow a very similar format. We just have to adjust the directions that we're moving. So if I want to do the upper right-hand corner, this is still moving upwards, but I would need to switch this to be plus to move right instead of left. And now when I run this, we can see, okay, we've got 2 of the 4. Just have to do this a couple of more times. So now I'll go down and to the left by switching this to be negative. Ooh, okay. Maybe my base case is not small enough, I don't know. And then down and to the right would be positive in the x direction and negative in the y direction. Should be the... This one doesn't look exactly like the picture you were given, but it's pretty close. I think this one's more detailed, honestly. I think the picture you were given maybe stopped a couple of layers sooner than this one did. Perhaps if I tweak my base case a little bit, I might get one that looks, well, okay. So tweaking the base case just determines how detailed. Yeah, that's pretty good. Yeah. I think we're, you know, on the right track. Again, if you have these factors off by a little bit, that's not what I'm concerned about here. If you have these numbers off by a little bit, I think a lot of students said half length divided by 2 instead of divided by 3. I don't care. That's not what's important to me, right? I am fully aware of the fact that if you had to do this on an actual computer, that you could tweak the numbers until you get it right. I am more concerned about the structure, the recursive structure specifically. Yep. It is a fun little program to play around with, though. Does anybody have any questions about this problem? Yes. Yeah, how is half-length updating? So that's a great question. We start with the big square in the middle, so that's when half-length is at our biggest. And every time we move a step down, it's getting divided by 3. So from here to here, the half-length is being divided by 1/3. And then from here to the next biggest square down is being divided by 1/3 again. And then the next biggest would be 1/3 again. So it's always just being reduced by a factor of 3 every time. But you can change that if you want your squares to be different shapes or sizes. Then you can, of course, tweak the numbers, and it looks a little different if you only divide it in half, for example. It takes longer to hit the base case, so I see more details, right? It's not shrinking as fast. Draws more details, draws more squares, and also overlaps, whereas it didn't do that before because not scooching out enough. But arguably looks cooler in my opinion. I don't know. Debatable, I guess. Subjective. Good question, though. Any other questions on this problem? Any other questions about what we've done here before we do another one? Yeah.
Could you explain the difference between like half length and half carpet length, and what the half carpet length is doing?
So this is just, so down here, we're in the main method. The main method is the entry point into the program. So this is where we start. This is the very first line of code that gets executed. This is just kicking things off. This is just saying this is what we want the size of our first square to be in the middle. And then all of the other sizes are based on this initial size. So it gets divided by 3 or 2 or whatever value from there. But this only happens once. So, this is just the initial one. The fact that it's just a variable name. I can call it whatever I want, right? This isn't a very good variable name, but still a variable name. Call it whatever I want. Yep. Question in the back. Okay, so if we look at the image, I'm given the x and y position for the center part of this square, and as well as the half width. So I know what the half width or the radius, I guess, of the square is, right? So I want to know how to get from here to here, the center point of this square, which is the next one that I wish to draw. So in the x coordinate, I'm moving over one half width, that gets me to the edge of the square, and if I move over one more half width, that gets me lined up with the x coordinate that I wish to be on. And for the y coordinate, I move up one half width, that gets me to the edge of the square. One more half width up gets me to the y coordinate that I want to be on. So I'm subtracted 2 half widths in the x direction and added 2 in the y direction to get up here. Does that answer? Cool. Awesome. Yep. Any other questions on this one? I thought I might have saw one more hand. Yeah. Great question. Thank you for asking that. So no, you do not need to have the standard draw methods memorized. I did not include them here because you're on the computer. You can access them, however you need to on the computer. But on the exam, if I asked you this question on the exam, or when this question was asked on the exam, we told you that there's a method called standard draw.filled square that takes in 3 parameters and said we want you to use it on this problem. And I will do that for anything that you need on the exam. That does not mean I'm going to give you all of standard draw. That would be a lot of stuff, and you're not going to need it all anyway. I'm only going to give you the parts that you need. But if you need to do stuff with scanner, I'll give you that stuff too, or anything else that you might need. I'll give you those. That's actually a big part of this exam, this idea that I can give you I can show you a method, right, that exists. You maybe have never seen it before or never used it before, but if I show you this method, say, hey, this method exists, here's the parameters that it accepts, here's what it will do for you, and then say use it, you should be able to do that. That's programming. That's what we're trying to teach you how to do. So, great question. Yes, I will absolutely provide you that info on the exam. Are we still talking about this problem or a different problem? If anybody has questions about this problem, I'd like to do that first. Yeah. Well, you'd have to refer to the documentation. I think that is in fact true, and I think that was a conscious decision that they made when they created it to keep things consistent. But I don't think it would have to be that way if they wanted to, have the first 2 parameters be the center point sometimes and something else a different time. They could have. That wouldn't be very nice. It would be a mean thing to do to us programmers. So I think they intentionally chose to keep it consistent. Yeah. Question about this or a different one? Okay, anybody else? Any last call on this problem before we go somewhere else? All right, go ahead. Yeah, which problem do you want to see?
I was thinking about question 5.
For the code writing?
Right, yeah.
Okay.
In this one, I can finish the code for int a goes to this one. The question, the requirements is making us to think about any input of any value could be for it.
Correct.
Yeah, so I'm thinking is there a way to have a scanner stuff included in this one? How can we deal with scanner when we're dealing with both methods?
Okay, well, so let me address the second thing that you said first. You can use scanner here if you want to, but I mean it's very much not included on purpose. You don't need scanner here. I think to address the problem that you were getting at first, I do expect this to work for any array, for any value. So if you write code that works, I should be able to come up and give you an array that's got, a bunch more values in it, and your code should still work, right? That's kind of the point that I'm trying to make. I don't think scanner is what we need to help us with that problem, though. I think we just need to be careful about how we write this code. So let's take a crack at this problem and see if we can't solve it. I think it doesn't say, it actually says it's not necessary to use recursion, so I wouldn't personally use recursion on this problem. I think loops are perfectly fine. Could you do it with recursion? Yeah, I definitely saw students try to, but it made me feel really bad for them that they tried to, because that just sounds not like a lot of fun to me. I would probably prefer to use a loop here. So, okay, I want to go through every element in this array and see how many times this element shows up. So before I've looked at anything, I know that I've seen it 0 times, right? So I'm going to make a variable to keep track of how many times I've seen this value in the array. And it starts out at 0. You actually could use a for each loop here if you wanted to. I think that would be nice. But if you want to do this style of loop as well, that's also okay. I think they'll both be all right. We're now just going to fetch a value out of the array and see if it's equal to the one that we're looking for. And if it is, I'll bump that counter up by 1, indicating that I've seen that value one more time. And then once I've gotten through that loop, I will have visited every single value in the array, incremented the counter if I need to. So by the time I've gotten through that loop, I should have my answer. The answer is whatever value is in count. So if I run the code as written, it should hopefully find that number 1 appear twice in the given array, which it does. But to the point that we were making before, if I come down here and add a whole bunch of other values, right, it should still work. So I didn't add any more 1s, but I did add a whole bunch of other stuff. Should still tell me 2. Okay, well, if I come in here and add a whole bunch of other 1s, it should also still work, right? So how many 1s do I have now? Too many commas, actually. There we go. So apparently I have 7. 1, 2, 3, 4, 5, 6, 7. Yeah, it works. So the point here is really that it depends on making sure you do things like this. If you looked at this problem as it was originally given to you and said, oh, I'm just going to write a loop that goes from 1 to 3, that's bad. Because then I'm going to give you an array with 10 things in it, and this breaks. So don't do that. Use the length. Ask the array how many things it has in it. That's the more important thing to think of. Yep. This will work for any array you can conceive of and any value you want to look for. Questions about this problem? Okay. Where to next? Yeah, go ahead.
Do you have to know when you break up a word into characters and then go through each character?
Break up a word into characters and go through each character. I know that we've mentioned characters a little bit, and I'm struggling to remember where they would have popped up. Studio.
On the last assignment, you wrote the code for us.
Yeah, I mean, so I think you should be aware of the fact that strings are made up of characters, but I don't think I've asked you to write code using characters, and if I have, it's been very minimal, so I would not expect it to be something that's going to be emphasized on the exam.
If you have to count which character in a string.
If it's something that I've asked you to do in Studio, then yes, but you know, I'm trying to make up problems that are representative of the things that we've done in class on the assignments, and so if, you know, I'm not looking for the one problem on characters that was buried in the Studio to grill you on the exam. That's not my goal or intention. Yeah. In the red there.
I was wondering, a recursive substructure, is it just like everything except for the substructure? Like, is that it?
You're on the right track. The recursive substructure is the idea that I can define a recursive method in terms of itself. So when you're being asked for a recursive substructure, or trying to think about what the recursive substructure is for a problem, I am quite literally looking for if the recursive method that I'm writing is called function, right? I want to see function of n is equal to something. Whoa, hey, what are you doing, Eclipse? Is equal to something function of, right? I want to see that the function is defined in terms of itself. That is recursion. That is the recursive substructure. I want to see a single expression that says the function of n is equal to whatever the recursive substructure is. So for factorial, what would that be? For factorial, which I believe is the example that we did in class, that would be n times function of n minus 1. This is the recursive substructure of factorial. The general form. This works for all values of n, all positive values of n, right? Does that answer your question? Cool. What's next? Yeah, go ahead.
Can you go over question 8
Question 8
of code reading?
of code reading. Yes, awesome. All right, cool. This is a complicated one. Yeah, we went through this one last section too, so I'm happy to go through it this time as well. It's recursive, I believe. Yes. So this is a recursive method. It does do some recursion down here. I think taking a look and trying to identify the fact that it's recursive off the bat is a good idea. I think also trying to identify that this is kind of looking like the base case right here is a good idea. If you're practicing, if you're prepping for the exam, I would highly, highly, highly encourage you to go through these with a debugger, because that's quite literally what I'm asking you to do on the exam. If I was approached with this problem on the exam, I'm going to pretend I'm the debugger. I'm going to write down every variable that I come across and update it for every line of code that gets executed, right? But since we're actually sitting at a computer, I'm just going to go ahead and use the debugger, starting with, I still have my breakpoint set even from last time. So I've got a breakpoint set down here for line 21. We'll go ahead and start up our debugger and begin walking through this problem. The parameters to the method include an array as well as two values, one that's called, I believe, location and one that's called count. So we're going to start by examining, we're going to start by examining the execution of this method, taking in this array with these values. Okay. If I step into the method, you can see the first thing that it asks us to do is to print out whatever value is at the given location. So that's as easy as fetching the value of position 1 in the array, which is t, right? T. So t is the first thing that I expect to see. Then we're doing some arithmetic. I'm going to compute the next value as my current location times 3 plus 1. So that would be 3 times 1 is 3, plus 1 would be 4. All right? If the current location is even, we're actually going to ignore this value. Do you see that? So we compute this value, and then we say, if the location is even, well, forget about that and just use this instead. So what does that mean practically? That means that if my location is odd, I'm going to do this computation. If location is even, I'm going to do this computation, right? Again, I'm just saying that because that helps me as a human being, easily understand the execution of this code, helps kind of simplify at least the top part of this in terms of my understanding of what's happening. So because location is odd, we're actually going to skip this and move down here and check the base case. In fact, we see location is 1. That's going to trigger our base case. So we're going to return values at location of 0. Go ahead and step down to that point. So I'm going to return E. That E is going to get returned here. So the result of this method call is a string containing the letter E, which is then going to get printed out by this print statement. That's how this particular one is going to end. So you can see here's the E being returned. And then if I step one more time, it gets printed out. So the result of the first method call is TE. But there's another one, and I'll walk through this one as well. This one is a little bit more complicated. So we're using the same array as before, but now we're using 4 as our location and our value. So let's see how that changes things. I'm going to print out the value at location 4. All right, so 0, 1, 2, 3, 4. That gives me the R. So R is the first letter that I expect to see. And we already kind of figured out that if the location is odd, I do this, and if it's even, I do this. And it is even, so I'm not going to bother wasting time figuring this math out. I'm just going to say, all right, the next value is going to be 4 over 2, which should give me 2. There it is. There's my 2. I have not hit the base case yet. Location and count are both 4, so not hit the base case yet, which means we're going to jump down and do some recursion. The array remains unchanged. I pass in 2 for my next location, and I decrease count by 1. So we should see those parameters get updated. There's the array, location is 2, and count is 3. But remember, that old recursive call is still sitting there waiting. All right, so now I'm going to print out the value at the location of 2. That's going to give me an I. Here comes the letter I. 2 is even. I know 2 is even, so my next value is going to be this one, right? So next is going to be equal to 1. Have not hit the base case yet. Location is 2, count is 3, so these are both false, which means we're going to do more recursion. But take a look at what we're doing. I'm saying values, that's my array. Next is going to be equal to 1, and the count is going to go down by 1. It's going to be 2 this time. But wait a second. We've actually already seen what happens when the location is 1, correct? That was the first method call that we did. So you could actually take a big shortcut at this point in time, if you wanted to, and say, I think the next letters that are going to be printed out are T and E. And you would actually be correct. The result for the second method call is RITE. That is the result. But if you would like to verify that, you can step through the execution again and see that the next value, it gets computed. It actually does not matter because we're about to hit the base case down here. So there's the T that got printed out. We compute the next location, but since we hit our base case down here, it says just go ahead and return the value that's at location 0, which is the E. That E then is going to get passed all the way back up the stack until we hit the main method, and will then get printed out by this print statement right here. So after we step through the remaining method calls, we can see that the only thing left to do is to print out that letter E. That's going to be the result of the method call on line 23. This is one of the trickier code reading problems, I think, that you've been given. So I tried to explain my thought process in as much detail as possible, how I would approach the problem. Please use the debugger, though, if you're ever unsure. Quite literally, that's how I would approach it. Pretend I'm a debugger, write down all the variables, keep them updated as I go along. Any questions on this problem? Okay. If there aren't any questions on this one, I'm happy to do another one. I see one up there. Yeah. Number 9 for which one? Code reading? Okay. Perfect, yes. So this one asks you to use the substitution method. All right, let's talk about the substitution method. I did an example of this in class when we talked about recursion. Happy to go through it again now because it is definitely something that you could see show up on the exam. The substitution method is really, I'm asking you to show me the execution of a recursive method. So when you see substitution method, I'm asking you to show me the execution stack all the way down to the base case and then all the way back up to the main method. That's quite literally what the substitution method is asking for. So let's walk through it. I'm going to type it out just like I would do on the exam, and then we can use the debugger to help us see if our answer is correct or not. So to do the substitution method, this is our starting point. So that's what I'm going to start out with. Function of 4 is equal to what? Well, let's follow it through the code. So I plug in 4 for k. That is not greater than 25, so I'm going to jump down here. And that tells me that I need to do function of 4 times 2, which is 8, minus 1, which is 9. But be careful about how I write this out, right? Function of 9 plus 1, because there is, in fact, some addition to be happening over here, right? So I can't evaluate this until I know what this is, until I know what the function of 9 is. So I'm going to go down a line and say, all right, the function of 9, I'm sorry, that should be 7, shouldn't it? It was 4. 4 times 2 is 8 minus 1. It should be 7. Sorry about that. Okay. So now we're going to plug in 7. 7 is still not bigger than 25, so I'm going to come down here. It's going to be function of 7 times 2 is 14, minus 1 is 13, plus 1. All right, now we have to go off and figure out what this is, right? So if I plug 13 in, still not bigger than 25, so we're going to come down here, and I get 26 minus 1, which is exactly 25, correct? I don't know why I put semicolons there. Doesn't matter. Now be careful, it has to be bigger than 25, so we haven't actually hit the base case yet. 25 is not bigger than 25. So I'm going to get 49 down here. Plus 1. And now finally we have in fact hit our base case. If I plug in 49 for the value of k, that is bigger than 25, and it just says that that answer is going to be 49. So I know what this is. But we're not done yet. We're not done yet. We actually still have to do the substitution part of the substitution method. The reason why it's called the substitution method is because now that I know what this value is, now that I know that function of 49 is equal to 49, I'm going to take this value and I'm going to substitute it into this expression right here. And that's going to allow me to figure out what the value of this is, which I'll then take and substitute in here, and on up the chain. So let's go ahead and do that. The function of 25 is going to be equal to 49 plus 1, which is equal to 50, right? The function of 13 is going to be equal to 50 plus 1, which is equal to 51. Function of 7 is going to be equal to 51 plus 1, which is 52. And then finally, did I skip one? No, I think I did it. Function of 4 is equal to 52 plus 1, which is equal to 53. So substitution method says work your way all the way down to the base case and then substitute the values back in. This is what I would expect the final answer to be. If I actually run this code and print it out the result, I would expect it to be 53, which we can verify. There it is, there's the 53. Or even better, we could use the debugger, because the substitution method is, while it certainly will show you what the final result is, I'm more interested in the substitution method to show the execution of the recursive method. That is why I care about the substitution method. So yes, getting this final number correct is important and good, but so is all of this other stuff. So using the debugger, we can verify that it's actually executing this way. Set a breakpoint on line 26 and fire up the debugger, and let's see what happens. So I step in, here's my value for k is equal to 4. Should be recursive. All right, another call where k is equal to 7, just as we predicted. Still recursive. K is now 13. We're proceeding right through. K is now 25. Still have not hit the base case. K is now 49. Here's our base case. We've hit our base case, and if we look at the execution stack, we can see all of the method calls that I expected. Here's the one for the base case, and then k equals 25, 13, 7, 4, and my main method, all just sitting here waiting. And now we're going to work our way back up. So this is going to return 49. All right, 49 plus 1 gets me 50. 50 plus 1 gets me 51. You can see the execution stack is shrinking as the methods finish. and return their values now that the substitutions are taking place. Until finally we return back to our main method. We can see the 53 is the value that got returned and printed from our original method call. So if I ask you to do the substitution method, this is what I'm looking for. I want to see all of the steps of the recursive execution, down to the base case and then back up to the main method. Yeah, question. I mean, I'm not grading you on the format, but this is the information that needs to be conveyed. So as long as I can read your answer and understand the execution of the recursion, then that's what I'm looking for. Any other questions on this problem before we do another one? Still got plenty of time left. Any questions on this one? Okay, where to next? What practice problem would we like to see next? Go ahead.
Can we go back to the exercises we did on YouTube?
Okay.
There's an animation one on about the balls, and we use the array to update the x and y axis
Uh-huh.
animation. And while we were doing it in class, we were trying to generate random numbers to fill in the arrays first, and then we generated another variable every time. Yeah, this one.
Mm-hmm.
So, I was wondering because in our positions we all have mascot random to fill in the array, and then we add new velocities. So, when I was reading it, I suppose that the animation at every second is going to occur in different parts on canvas, but in fact it is showing continuously. So that is where I'm confused.
Well, so the computers are very fast. The computer is able to compute the updated positions of all of the objects on the screen and show them to you fast enough that your brain interprets it as motion. So that is this process down here. It looks like it's doing a lot of work, but computers are extremely fast.
Yeah, I understand this process. What I'm confused is that if they are continuous, shouldn't they be like for example, position I plus 1 equals to position I minus I 0 and then plus velocities. But they are just generating different and very random numbers.
So when is this happening? When are these random numbers being generated? How many random numbers am I generating per ball?
Like 2.
4 actually. Two for the position and 2 for the velocities. But how many times am I doing that?
Like every time you like how long the array is.
Once per ball.
Yeah.
So I do this once per ball at the very beginning. These random values are just being used for the initial XY coordinates and the initial velocities.
Yeah.
This work that is being done down here is not random at all. I'm not using math.random at all. In fact, once I enter this while loop, I have no way of getting back up here anymore. So once I've started the animation, there is no more randomness involved. This is just to give us some initial values to work with.
Oh, so is it saying that first the velocity is not changing every time because it is set up for each single ball? Like they might be different, they might not be, but it's no longer changing after the animation starts.
The only time the velocity is going to change after the animation starts is if it bounces, in which the sign would flip. But otherwise, yes, the velocity remains the same. You don't have to do it that way. You certainly could change the velocity during the animation. That's just not how this particular code works.
Oh, so I see. Like every time, the first it clears the canvas and then updates every single ball, and then it shows it on the canvas that we see, and then clears it.
All within a fraction of a second, yes.
Oh, I see. Thank you.
Yeah, all within milliseconds. Yep, it's doing that hopefully 30 to 60 times per second.
I see. I was wrong because I thought that the one single array is the update of one single ball.
I see, yeah. Gotcha.
Thank you.
Yep. What's next? What other questions do we have? Yeah, go ahead.
Can you go over question 6 on the again?
Sure.
Just like how to approach it.
Yeah, absolutely. Question 6. All right, yeah, this one is another somewhat tricky one, although you have a big advantage with this one in that I've given you some iterative code. So this was a point that I have tried to make a lot with recursion and loops. They're both used to do the same thing, which is repetition. So loops are used to repeat things. Recursion is also used to repeat things. So I explained that this is a method used to compute square roots called the Babylonian method. You actually don't need to understand how the Babylonian method works at all. You don't even need to understand that this is computing square roots to do this problem. This is more of a problem about, can you recognize, if you're given a while loop, how those pieces would map onto a recursive solution. That's really what this problem is about. So let's try it. That's not to say that it's easy. I know I'm making it sound simple. It's not. So let's start working through this and talking about how you might approach this problem. It does tell you straight up that you're going to have to use a helper method. So let's talk about that for a second. What are helper methods used for? There's two good reasons. There's probably more than two, but there are definitely two reasons that we've talked about for using helper methods. Yeah. Correct, yeah. So we use helper methods, I think kind of what you're getting at, we use helper methods to isolate the recursion. So recursion is used to do repetition. Anything that only needs to happen once, which is what you were describing, just creating variables, setting up a loop or whatever, that stuff only needs to happen once. So if you try to do that stuff inside of a recursive method, as some of you have probably done and found out the hard way, it can lead to some problems. So using a helper method allows us to keep the stuff that needs to happen once in the non-helper method, separate that out, and then the helper method is actually going to be the recursive one, the one that's repeating a whole bunch of times, the one that's doing our repetition for us. What's another reason why we like to use helper methods? You kind of actually also gave me the second reason with your answer a little bit. With the helper method, I have the ability to make that method however I want, right? So I can add additional parameters to help me track additional pieces of information that I might need. This is an important concept, right? With loops, we don't have to do that because it's all within one method. So I can just create variables and use variables within the method. But remember that when we're using methods, I can't actually view variables outside of the method they're created in. So if I want methods to be able to communicate with each other, we have to use parameters. So having additional parameters or more than one additional parameter allows our recursive method to keep track of more information. So let's start to try and piece this together. I'm actually going to come down here and stick in my helper method since I know I'm going to need one. Square root helper. And let's start by talking about these parameters. You're almost always going to want to keep whatever parameters you've started with. So that's pretty simple to just copy that one down. But then for the other parameters, I'm actually going to look up here at this one. Inside of the repetitive part, I'm working on the helper method. So I'm really focused on the repetitive part of this code, which is the while loop, and think, okay, what variables is this loop using? I see that, yes, it is using x, but it's also using variables called x old and x new. And I think I'm probably going to want to include those as parameters. So any variables that I'm seeing used inside of a while loop, if I'm trying to convert this into recursion, those are probably going to end up becoming parameters for my helper method. So I'm just going to come down here and add them in. X old, double, x new. Do I know what those variables do or what their role is in terms of computing the square root? Not necessarily. I just see that they're being used in the root inside of that while loop. If I wish to create a recursive implementation of this, that means that I'm probably going to have to use the parameters to pass that information instead. Okay. We can now actually come back up here and talk about this method. Remember, the helper method is our recursive method. It's going to be doing the repetition. Anything that doesn't need to be repeated is going to happen, it's going to happen one time, and it's going to happen here. So if we scroll back up to this code and we examine, what isn't being repeated, it's this stuff. This stuff is only happening once, creating these variables one time at the very beginning. Well, these became parameters. So instead of creating these as variables, instead what I'm going to do is I'll call my helper method, and I'll pass in the parameters. So x is just going to come through as x. But then the initial value of x old, I can see is also set to be x. So I'll just go ahead and say that's going to be x. And the initial value for x new is set to be x divided by 2. So I'll go ahead and set that here. Okay? So I've done anything that just needs to happen the one time, which is basically, in this case, variable initialization. I've done that here. This is now going to be responsible for doing the recursion, for actually doing the repetition. So I'm going to look up at this while loop. I'm going to look up at this while loop. The while loop says, while this is true, keep going. We're actually kind of used to saying a little bit of the opposite with recursion. We're used to saying, if this is true, then this is my base case and I'm going to stop. Right? That's kind of what we're used to saying in recursion. Well, I could actually take this and convert it to a base case pretty straightforward, right? Again, I'm not even concerned about what this code is actually doing. No loops allowed. We're doing recursion, but I can very easily switch that to an if and say, all right, if this is, I did flip the sign. I think that's important, right? Here I'm saying if this is true, keep going, right? Here I'm saying if this is true, stop. So that's why I flipped the sign. That's why flipping the sign was necessary down here. What's my answer? I guess if you didn't want to flip the sign, you could do it slightly differently. You could leave the sign intact and say recursive stuff here, and then put your base case in the else. That would also be perfectly okay, right? However you want to do it, potato, potato, both get you the same place. Regardless, when I've hit the base case, we have to say what the answer is. What's my answer? What's the value that's being returned? So think about what happens up here. Up here, this loop stops, and this is the answer that I'm returning, the variable called x new. So in my base case, wherever that happens to be, I'll just return x new. And then here I have to do my recursive stuff. Well, that's going to start out by doing anything that's in the body of the loop. So I'm quite literally just going to copy not the entire, what did I do wrong? Sorry. I'm not going to copy the whole loop. I'm just copying the stuff that's inside of the loop, right? Just copying the body of the loop. We no longer have the while loop to enforce the repetition for us. We're using recursion for that. So after I've performed these tasks, that's where our recursive call is going to come in. X old, x new. This just keeps the repetition going. Make sure to stick a return statement out there in front. And I think this will work. Again, I'm not spending time talking about how the Babylonian method works. I don't care. I think it's pretty cool. I think it's pretty interesting. This is quite literally how they used to compute square roots in ancient times. It's called the Babylonian method for a reason, right? It's a pretty cool way of doing things. Works kind of well. But the bigger question that this problem was asking you is, if you see a loop, can you envision how that could be turned into something recursive? And I think the opposite's also fair. If I give you something recursive, could you envision how to turn that into a loop? I think that's also a reasonable thing to think about, because both recursion and loops are used to perform repetition. And if you want to test this out, there are some things down here at the bottom to compute the square root of 5. You know, this is using the iterative version, and this is using the recursive version. You can see that it actually travels the same path to get there. One uses a loop, one uses recursion, but they both hit the same sort of intermediate points. And then perhaps less relevant to the exam, but still somewhat interesting, at least to me, we can use the official, math.square root that's given to us by Java, and compare that to the answer computed by the Babylonian method. You'll see that the Babylonians actually did a pretty darn good job. They got it right all the way up until there, and at that point we start deviating from the official Java square roots, right? But that's pretty good for ancient times, I think. Be able to compute square roots like that. Any questions on this problem? You've definitely hit on some of the more tricky ones here, but are there any questions on this problem before we switch to a different one? Question up there, yeah. Yeah, so why did I change it from greater than to less than? I mean, it's personal. I could have done it this way. So, right, I actually switched it back. Maybe I did it too fast. I could have done it both ways. Could have done it either way. I could, if I switch it to less than, then all I need to do is move this stuff down here, right? And then put the base case up here, right? I can swap the order all I want, doesn't matter. As long as I'm consistent. Yes? It's used as a computation in this term right here, so we do need it. Yep. That's a very good question, though. I understand why you asked that. It's like, do we really need it? It is right there. If it weren't right there, though, I think we could take it out. Good question. Any other questions on this problem? Yeah, in the back. That sounds like a typo thing to me. I don't know. You can come talk to me after class. Maybe I can take a look. We have about 18 minutes left in class, so I certainly have time to do, I think, at least one more practice problem if somebody's got one for me. Might have time to do a couple. Yeah, go ahead. Number 9. All right, cool. Yeah, this is a good one. So this one does say you have to use recursion. Have to use recursion, right? Again, if I don't say you have to use recursion, then you don't have to use recursion. Use a loop if you want to. But this one, you got to do recursion. And so we want to write a recursive method to figure out the number of digits. So you can see if I give you 1,000, that has 4 digits in it, right? If I give you a bigger number, it has more digits in it. Generally like to start with the base case. So you think about the base case, it's usually going to be a simple case, right? A simple situation that we find ourselves in. So what's a simple situation you think we could use for a base case here? Number of digits, simple number of digits would be a case when I don't have very many of them, right? Probably values that only have 1 digit would be a good base case. 1 digit. So think about how we might check for that as part of a base case. This problem doesn't say that you're only going to be given positive values. I don't think I actually cared that much about whether you worried about negative values or not when this problem was given on the exam. But if x is less than 10, I know how many digits it has, right? It has 1 digit. If x is less than 10, it has 1 digit. And if you're worried about negative numbers, okay, take the absolute value. I'm not as worried about that. That is not the biggest concern that I have for this problem, right? More worried about the base case and the recursive step. Okay. So, this is the tricky part. If it doesn't, if it's greater than 10, we have to figure out how can I do this recursively? What's the recursive substructure, to go back to a conversation that we were having earlier? So, if I have the number of digits for, 1,000, that's going to be equal to, something that includes number of digits where the value inside of the parentheses here has to be different. I can't plug in 1,000 again, right? That would just spin me in circles. So it has to be something that takes me closer to the base case. So if I'm starting with 1,000 and my base case is less than 10, what about just chopping off one digit? What if I said that the number of digits in 1,000 is equal to 1 plus the number of digits in 100? Would you agree with that statement? Yeah? That's the recursive substructure. That's the recursive substructure for this problem that we are currently solving. If you wanted to, you could extend this example out, right? The number of digits in 100 is equal to 1 plus the number of digits in 10. Right? And on until you hit the base case. If we want to generalize this out, the number of digits then in some number n is equal to 1 plus the number of digits in n divided by 10. You see that relationship? I'm just dividing by 10 every time. That makes sense based on what a digit represents. Anytime a value has an additional digit, that means I've gone up an additional power of 10, right? Included an additional power of 10 into my number. So it makes sense that I would be dividing by 10 to count how many digits I have. Turning this into code is quite simple. We're actually just going to say return 1 plus x divided by 10. That's it. I think that's it. We can test it. There's some examples down here. Should say, oh, I forgot to call the method. Whoops. Sorry about that. Should see 7 and 4. There we go. But again, if you're having a hard time understanding exactly how this recursive method is working, use the debugger. The debugger is a great tool to help us understand what's happening in our code. If I can find, here we go. So here I am, I'm about to do it for this big, large number here. Step into, all right, it's not less than 10. Here, where's my value for x? There it is. Not less than 10, so it's going to be recursive. And you can see 1, 2, 3, 4, 5, 6. Okay, still not less than 10, so more recursion, more recursion, more recursion. 12. All right, here we are. Now my base case. Remember, each one of these method calls has a 1 plus sitting out in front of it. So from here, you can honestly see, all right, 1, 2, 3, 4, 5, 6, 7, right? But the computer actually has to execute all of that. So there it returns the 1, adds a 1 to it, adds another one, adds another one, adds another one, all the way back up until we hit the main method, shows us 7 as the result, and then gets printed out. And it'll do the same thing for 4. What questions do you have on this problem? Any questions? Okay. We do still have about 10 minutes left. I am a little worried that I won't have enough time to get through another full problem with the time that we have left. So I think what I might do instead is go ahead and wrap it up and stick around. I will stick around if you have any other questions. You're welcome to come up, talk to me after class. The TAs will be in class on Wednesday and Thursday, so if you want to come to class on Wednesday and Thursday to get exam help, you can. There is no studio, though, so we're not going to be taking attendance or anything like that. Just exam help on Wednesday and Thursday. Otherwise, that's all I've got for you for now. Good luck studying, and I'll see you at the exam on Thursday.